The topic of this presentation is vibrational energy in its relationship to heat and work in the first law of thermodynamics. The mass on the spring is not, as it's shown here, in this physical form, relevant to solution thermodynamics or protein thermodynamics. But the mass on the spring is an incredibly important model for a fundamental property of molecules, which is the fact that bonds and angles vibrate. Like the mass on the spring, once you set it in motion, you'll have a continuous interconversion of potential and kinetic energy. The bonds essentially undergo the same kind of vibrations, and the physics of that, bonds, both their lengths and their angles, will undergo the same kind of vibrations. And the physics of that is nicely described by the equations that describe the oscillation of the mass on a spring. So we're going to go through the mathematics here quickly. It's fairly simple. You've almost certainly seen it before. The key point is that the spring has some equilibrium position. So at some distance, at some length of the spring, there will be no net force on the mass. Now, if you pull on the mass, right, so force would be required to do that. If you exert a force on the mass and pull the spring to a larger extension, you will need to do work. You'll have to do work against the restoring force of the spring. To move the mass to a positive position, the force would have to be exerted in this direction. In this case, the force on the mass would be positive as you do the work going out. And then when you get to this position, the force on the mass would be in the negative direction in this coordinate system. And at this position, the force on the spring is in the positive direction. So if you were to take the mass on a spring at its equilibrium position, pull it out, and then hold it in this extended position, there would be no net force on the mass, right, if it's not moving. So again, if you exert a force that basically opposes the restoring force of the spring, that's the only way you can get zero acceleration, is by those two forces to exactly balance out so that there's no net force on the spring. In this fully extended position with no if it's the mass is still and not accelerating at this fully extended position, that means the force on the spring, which is, again, the mass is pulling the spring out in this direction, that would be, the force on the spring is a positive force, kx. The force on the mass, of course, is exactly equal and opposite to that, negative ks. So this is the basic mathematics of it. The critical point here of this so-called Hooke's law spring is that there is a linear relationship between force and extension. In any system, a spring characterized by this kind of first power linear relationship, right, so that the force is linearly proportional to the extension of the spring and related by a force constant K. This is called a so-called Hooke's law spring. And again, as we'll see shortly, the importance of this for molecular physics and solution thermodynamics is that bond vibrations, both length and angular vibrations, are modeled as Hooke's are well modeled based on the Hooke's law spring, the physics of a Hooke's law spring. So what we want to do now, of course, is calculate the amount of work done that was as this thing begins to move, right? And so as the spring, how would we get this system to move? Well, the first thing we would do is we do this extension, and then we would basically let it go. And at that point, the spring, right, if we remove, take away the force that's counteracting the force of the spring, there would now be a net force, specifically the force exerted by the spring, pulling back in the negative direction. So when we let go of the mass, the spring exerts on it a force negative kx. On the other hand, when we pulled the mass out from its equilibrium position, we had to exert a force on the mass. that is equal to positive kx, right, the force on the mass. So in the end, the work done in extending the mass out to this position is going to be exactly, the work done on the mass by an external force and extending it out to this position will be exactly equal to the work done by the spring in moving the mass back to this position. Again, to every action, there is an equal and opposite reaction. Another window on that is that energy is conserved. Whatever work we do pulling this out here, that is potential energy stored in the spring. Because energy is conserved, these equations describe sort of how energy is conserved. We have to recover exactly that much amount of kinetic energy when the mass moves back to this point. So again, that's the basic process we're modeling here, an interconversion of potential energy from stretching the string to kinetic energy as the mass is pulled back and accelerated by the spring. So we'll start by calculating the work done in extending the spring to this maximum position. That will be the force on the spring, which is the force on the spring is a force in the positive direction. It will be equal to k, the proportionality constant, times the distance of displacement from the equilibrium position. And so we have a very simple integral. The work done in extending the mass is the integral of k x dx. In this case, the direction of propagation, we'll say, is directly parallel to the spring. In that case, the dot product reduces to just integral of x dx. We know that the integral of x dx is 1/2 x squared. So the total amount of work done in this extension process is 1/2 kx squared, going from x equals 0 to x max. And that, of course, gives us the potential energy stored in the spring at full extension as 1/2 kx max squared. So this is the potential energy of it's the potential energy of the spring in the fully extended position. And what simple harmonic motion involves is a continuous interconversion of that potential energy in the spring to the kinetic energy of the mass. So once you pull the spring out to this position, when you let it go, again, the work the spring does in bringing the mass back to the equilibrium position will be exactly equal to the work that we did in pulling the mass out to this most extended position. And so as the spring does work on it, that will accelerate the mass. It will increase the kinetic energy of the mass. When it gets back to the equilibrium position, the kinetic energy of the mass will be exactly 1kx max squared. Of course, at the maximum point of extension, there will be no kinetic energy, and the potential energy in the spring will be exactly 1/2 kx max squared. And at any point in this trajectory, the sum of the potential and the kinetic energy will be exactly, guess what, 1/2 kx max squared. At this point, as the spring passes through the center point, if it is just moving under its own inertia, it will have exactly enough kinetic energy to push the spring back to exactly negative x max, right? Because in the Hooke's law spring, forward and reverse extensions involve the same force relationship, and therefore the same amount of potential energy change is involved in going a certain distance either forward or reverse from the equilibrium position. So basically, when you're fully compressed, you have kinetic energy of 1/2 kx squared max squared. Fully extended, you have exactly the same amount of kinetic energy. In the middle at the equilibrium position, you will have, exactly the same amount of potential energy. In the middle at the equilibrium position, 0 potential energy, and exactly 1/2 kx max squared kinetic energy. But again, at any point in this oscillatory process, the sum of the potential energy in the spring and the kinetic energy of the motion of mass will be, guess what, 1/2 kx max squared. So this is a place that energy can be stored. Once the spring is moving, assuming it's frictionless, it will just go on forever that way. And again, that is the way that bond vibrations are modeled. That provides a very accurate model of the physics of bond vibrations in molecules. And so we will go on shortly and discuss that before moving on to those specifics. Let's just point out that this is yet another example of the first law of thermodynamics in action. We have shown another specific physical mechanism by which work can be done. Well, if this is a bond length or bond angle, it would be work being done on a molecule. And so heat or enthalpy can be stored in bond vibrations, and that vibrational energy is in fact a very important place where energy goes in, for instance, aqueous solutions. Now, in aqueous solutions, some energy will indeed go into the vibration of the, let's say, the OH bond, or the linear vibration of the OH bond, the angular. There also is angular vibration involving displacements, sort of a squeezing motion between the hydrogen atoms in the water molecule. But then you'll also have, in water solutions, you'll have vibrational energy stored in, let's say, more complicated molecular interactions that have to do with oscillations of groups of hydrogen bonded waters bumping up against each other based on van der Waals interactions. And so you'll have all sorts of vibrational-like energies that involve more complicated spatial and energetic interactions between the molecules. However, in any molecular system, some of the energy will be stored in the bond angle, in the bond vibrations, the length vibrations, and the angular vibrations. So we'll go on to that momentarily. Before we do that, let me just point out what I said earlier in a more graphical way. Again, just remember, when you're thinking, if you want to think about the math of this system, the force on the spring is going to be greater than zero, right? And when we're pulling the force on this, when we're pulling the spring forward to get to this position, this positive coordinate x, the force on the spring is positive. When it's right, to extend the spring to this position, we have to exert a positively directed force to hold it there. When the force, if we compress the spring to this position, we need to have a negatively directed force on the spring in order to hold the spring here and keep it, the force, the energy stored within the spring from pushing the mass back. Right? And so this is just a graphical way of making the point that the force on the spring is opposite, equal in sign, but opposite direction to the force on the mass, which when you're extending it, the force on the mass would be positive, as we said before. And when you're compressing it, the force on the mass would be negative. Okay, so now let's go on and think about how this relates again to molecular structure. As I said earlier, the relevancy is that bond lengths and bond angles effectively behave like Hooke's law springs. So the bond length will have an equilibrium position. At that equilibrium position, there will be no net force pushing the oxygen atom away from that position. But if you move the oxygen a bit towards the carbon, although the underlying physics of this involves rather complicated quantum mechanical things, it is well approximated by a simple Hooke's law force, where the effective force pushing the oxygen atom away from the carbon, if you compress this bond, the effective force pushing the oxygen away from the carbon is linearly proportional to the distance of displacement. And similarly, the effective force pulling the oxygen back to its equilibrium position is linearly proportional to the distance of displacement from the equilibrium position. And so what this means is that bonds will vibrate. They will vibrate with characteristics very similar to a simple harmonic motion. Quantum mechanics tells us that place to store energy will always, that motion, that place to store energy will always have some energy stored in it. Even at absolute zero, you have some energy stored in the bond vibration, and that means there is some degree of bond vibration even at absolute zero. As you increase temperature, you will go to more and more higher and higher energy vibrations. In molecules, those go up in quantized steps. A quantized step would mean that the potential energy has to be correspond to a discrete quantized increase, because the potential energy is proportional to the square of the displacement. That means as you step up in quantized energy levels, you will step between different degrees of extension. And so the first excited state would have some degree of extension. The second excited state would have a higher degree. of extension. And so bond angles, again, bond lengths behave as Hooke's law springs. I suspect you've heard something about this before. What you may not have heard is that bond angles similarly behave like Hooke's law springs. Quantum mechanical structure of a chemical group like this will establish some equilibrium position for the hydrogen atom, which is the lowest energy electronic configuration of the molecule. When you move the hydrogen atom, let's say roughly circularly, right? When you displace this bond, when you change this bond angle, when you contract this bond angle or contract that bond angle, effectively you get a restoring force that's operating on the bond angle that behaves again like a Hooke's law spring. And so in fact in molecules not only do you get bond length vibrations, you get bond angular vibrations. Now in complicated molecules like this, well, in molecules that have multiple atoms, more than just two atoms involved in them, what happens is you get things called normal mode vibrations. And so what's going on, what this has been, there's a well-defined science of this. Vibrational spectra are interpreted based on these normal modes. You can very easily measure what the vibrational characteristics of the normal modes are. There's a relatively simple physical theory that I go through in my undergraduate biophysics class that tells you effectively how to calculate normal mode, how to calculate what normal modes are and what their energies are. We won't go into that level of detail here, but I'll just I'll just explain what the normal mode is. Well, in a molecule like this, if the nitrogen moves, let's say in here, towards the carbon, that bond length will contract. In the meantime, at the same time, the NH bonds both have to expand a bit, and at the same time, the angle between the CN and the NH bond is changing. So basically, if we had just, let's say, an isolated carbon monoxide molecule, we could stretch this CO bond without changing any other bond lengths or angles. But when we put these chemical groups into a more complicated molecule, the displacement again of the carbon would affect this bond length, and it would also affect to some extent these bond lengths, and it would very clearly affect this bond angle, that bond angle, and this bond angle in here. And so because there's a restoring force on every one of those lengths and angles, those things all get coupled together mathematically, and what you see in complicated molecules are collective vibrations involving multiple atomic coordinates. And these things are called normal modes, coupled vibrations of multiple bond lengths and angles. But each one of these normal modes will behave exactly like the Hooke's law. They will also behave like the Hooke's law spring, and they will undergo simple harmonic oscillations. And in a aqueous solution that contains, let's say, an amide group, a molecule that contains an amide group like this, energy can be stored in these kinds of normal modes and will be stored in these normal modes. So here is a chemical group that looks a lot like the polypeptide backbone. It's a bit different because this is actually not, the nitrogen is not making a bond to the carbon atom in the next amino acid, but in this case we just have an amide group attached to a carbonyl group. But this is something similar in structure to the amide bond in the polypeptide backbone. Amide bonds are characterized by, they have a number of different so-called normal modes. There are two that are used in biophysical experiments that are worth sort of knowing about. One is called the amide 1 normal mode, and that is mostly the stretch of the CO bond. When that happens, other coordinates move around a little bit, but most of that oscillation takes place. There'll be smaller displacements in, let's say, the NH position coupled to that stretch of the CO bond. But that is a vibration that where most of the motion, most of the energy is actually stored in the movement, the extension of the CO bond. Second widely exploited normal mode of the amide bond is something called the amide 2 or the NH rock. That is the angular vibration of the NH group relative to the other things to which that nitrogen is attached. And again, when heat goes into an aqueous solution of a protein, some of the energy will go into exciting these kinds of normal vibrational modes, as they're called. However, the energy of these motions is quite high, right? The allowed vibrational states are quantized. The first excited vibrational state over the ground state involves actually a fairly big step up in energy. It's a number of times larger than so-called thermal energy, or KT. And therefore, in practice, when you put heat into a solution, because these are such high energy things, at least at thermal energies, relatively little energy are actually going to get. Some energy will definitely be stored in these vibrations, but it will be relatively little. Most of the energy will go into modes or places that can take smaller amounts of energy. Again, bond length stretches and bond angle oscillations are relatively high energy places, kinds of motions. And so some energy will go there at thermal temperatures and aqueous solutions, but relatively little. However, there's another kind of angular vibration that is really critical to understand because it does involve smaller restoring forces. It is a lower energy vibration, and therefore effectively more energy will be stored in this place. And this is something called the dihedral angle vibration. And this is schematized, the dihedral angle is schematized here. This is something called a Fischer projection. The basic idea here is that you have two sp3 hybridized atoms. This is sort of a rotated view. You have this sp3 hybridized B atom. One of the atoms attached to is the A atom. Over here you have the sp3 hybridized C atom. One of the atoms attached to is the D atom. If this is a single bond, which it will be if these things are both sp3 hybridized, you have relatively free rotation around this bond, and therefore effectively this CD, whatever H, the three atoms attached to the C atom can rotate relative to the three atoms attached to the B atom. The Fischer projection is supposed to be looking straight down this CB bond. And then you see the A atom and the two atoms attached to B here 120 degrees apart. And in this so-called staggered configuration, we see the D atom and the two other atoms attached to C now also staggered, also located 120 degrees apart. As we look down, again, this view is supposed to be looking from down here, basically along the bond axis. When the atoms attached to one of these two sp3, one of these two atoms bonded, one of these two atoms that are connected by a single bond, when the atoms attached to one of them are immediately in between two of the atoms attached to the other, this is called the staggered configuration. When we would rotate if we were to rotate this so that D was exactly aligned with A, that would be called an eclipsed conformation. So I'm going to leave the PowerPoint for a moment to go to something called a CDF viewer, a computable document format viewer. This is something produced by the people who make Mathematica, a widely used mathematical modeling program to do sort of effectively little mathematical animations. What this is shown here is this is supposed to be an ethane molecule. This little applet does basically is allow you to see what happens when you rotate what's going on now. We're rotating around this carbon-carbon bond, and so this is ethane, carbon-carbon, 3 hydrogens, 3 more hydrogens. As we rotate around the carbon-carbon bond, the hydrogens attached to the carbon, of course, rotate to one another. And so this is a configuration. Well, if we move it over here, this is a orientation view of this thing that looks much like the diagram on the right that I just showed you in the PowerPoint presentation. What we can do now is we can rotate this so that we're looking directly down the bond angle, and this now corresponds to the depiction on the left in the PowerPoint presentation. Again, this is something that's called effectively a Fischer projection. You probably saw it in organic chemistry, and now we can see as we look down the bond axis what happens as we rotate the hydrogens, as we rotate around that carbon-carbon bond. And again, so the eclipsed configuration has the hydrogens on one carbon immediately in between the two hydrogens on the other carbon in the so-called, that's the staggered configuration. The eclipse configuration is the one in which things both, in which the hydrogen atoms are sort of directly aligned. And if we rotate this back and see what's going on here, in this configuration, we get a little bit of van der Waals overlap between when the hydrogens are directly aligned, we have a little bit of van der Waals overlap between them. In practice, actually there is some van der Waals overlap even for the hydrogens, but in practice for the hydrogens, it's actually a very small degree of van der Waals overlap. On the other hand, if we put a carbon atom here, another carbon atom here and here in this eclipse configuration, where they were directly opposite one another, right? In an eclipse configuration, if these were two carbon atoms, we'd have quite a significant van der Waals overlap, repulsive van der Waals energy due to steric overlap. If we rotate them out to the staggered configuration, we would therefore go to a significantly lower potential energy state. Okay, so to go back to the PowerPoint presentation en route to wrapping up, just one more slide to be shown here, and that is now showing the energy profile as we rotate around the dihedral bond. And so this is showing the essentially the van der Waals energy between the atoms that are bound. What we're looking at now is we're looking at as we rotate around this, let's say, carbon-carbon bond, in this case the BC bond, how the potential energy due to van der Waals interaction changes during the course of that rotation. And what we're seeing is we get high energy peaks alternating with low energy valleys. The high energy peaks are, of course, the eclipse configurations due to the van der Waals overlap we just talked about. The low energy values are the staggered configurations that's shown here in these Fisher projections. Now, what does this have to do with vibrational potential energy? Well, anytime you have a potential well of this kind, assuming it is roughly parabolic, and in the same way that if we zoomed in on a small enough zone, if we zoomed in on a small enough region in this plot, it would look like a straight line locally. If we look at a slightly larger region, effectively we will always be able to find a region where the well is roughly, where the function looks roughly parabolic. In the case of vibrations, potential dihedral angle vibrations, it turns out those occur over a range where this potential well is in fact roughly parabolic. A parabolic potential well, right? What is this? This Hooke's law relationships tells us that the work done in moving this around, right? The work would be the force times the distance over which it's applied. The work then done to move it is exactly equal to the energy stored in the interaction. The potential energy plot is giving us exactly the energy stored in the interaction. The functional form of the Hooke's law relationship tells us that the potential energy function should be parabolic. Again, in a local region, it's parabolic. You put this all together, and what it means is you get effectively simple harmonic oscillation or vibration of the dihedral angles. And these are much lower energy vibrations than the bond length and bond angle vibrations, and therefore in solutions in molecules at room temperature, you get a lot of energy stored in these kinds of dihedral angle oscillations. Now, in practice, if you go to a non-metallic solid material, a lot of the non-metallic solid materials we're familiar with are actually made from biological polymers. Wood, for instance, is a biological polymer. In practice, at room temperature, there isn't really a lot of there's not kinetic energy in a block, much kinetic energy in a block of wood in terms of things actually moving around long distances. But of course, vibrational energy involves a continuous interconversion of kinetic and potential energy. And in practice, at thermal temperatures, a block of wood, a cotton shirt that you're wearing that has other kind of biological polymers, in those materials, the bulk of the thermal energy is stored in angular vibrations of this kind. So that wraps up the next, well, actually, this section of the PowerPoint presentation, treating, again, another important manifestation of the first law of thermodynamics, the principle of, another example of exactly how work equals heat, and what we call enthalpy in solution thermodynamics. In this form of enthalpy is vibrational energy.